My name is Amy, and today I will be discussing geometric explorations of the Arbelos and its auxiliary constructions. The shoemaker's knife is an inspired construction of three semicircles, first studied by Archimedes. My research explores the Arbelos and its property involving auxiliary tangent lines, circles, and triple tangent circle inscriptions on the basis of my own definitions of Arbelos properties using hypotheses generated from polygons, coordinate geometry, trigonometric laws, and algebraic manipulations. The simple sketch will yield startlingly beautiful results and leaves unanswered questions such as the arc formed from the centers of infinite circles. The Arbelos is simply a combination of three semicircles, and first we will introduce and construct the Arbelos. To construct the Arbelos, begin with a segment. Define this segment as a baseline. On the baseline, mark a point D. Choose two radii R1 and R2. Next, choose points A and B on either side of D on the baseline such that AD equals R1 and BD equals R2. Finally, draw two semicircles with centers A and B on tangent at D and cut the baseline at S and T respectively. Draw the semicircle with diameter ST. Label the center of the semicircle as M. Figure 1 depicts the Arbelos. By definition, segment GD will be the axis of the Arbelos. Segment ST will be the base. The shaded area represents the area, and the segments highlighted will represent the perimeter. Naturally, when exploring the properties of a geometric figure, we start with the basics, area and perimeter. These two derivations are trivial, as the Arbelos is simply a composition of semicircles for which the area and perimeter formulas are well known. From here, we arrive at the fact that the area A is equal to pi R1 R2, and the circumference C equals 2 pi times R1 R2. Note that R1 plus R2 is the radius of a circle having ST as the diameter, so C is equal to the circumference of the circle having ST as a diameter. After basic geometric explorations, auxiliary lines and curves were constructed for further investigation. So the first investigation was the axis circle, which yielded theorem 1. In a given right triangle, by triangle similarity, the transitive property and cross multiplications, CH squared equals to AH times BH according to this diagram. Consider triangle SGT on the Arbelos. Because ST is the diameter of a semicircle, and G is the point on the circumference of the semicircle, SGT must be a right triangle with axis GD as its altitude. Applying the property above, we obtain the following expression. GD squared equals to 4R1 R2, which will be applied in future proofs. Next, construct the auxiliary circle with diameter GD. Using the equation for the area of the circle with diameter GD, denoted by A prime, is equal to pi times GD squared over 2. Now, plugging in the previous value we found for GD, we yield the equation A prime equals to R1 R2 times pi, which is exactly the value of A. This dictates theorem 1, which states that the area of the Arbelos SGTT is equal to the area of the circle having axis GD as a diameter. Another theorem was obtained through the drawing of two auxiliary lines, GS and GT, and relates to points of tangent G. Let P1 and P2 be the points of intersection on the Arbelos between circle O and on the auxiliary constructions. By a proof that each of its angles is equal to 90 degrees, it is apparent that GP1 DP2 is a rectangle. It is known that the diagonals of rectangles bisect each other. Therefore, O is a midpoint of segment P1, P2, and segment GD, meaning that this equation holds true. This yields theorem 2, which states that the segments cut off by the Arbelos on the common tangents to its two smaller semicircles bisect each other, and their endpoints lie on the circle having axis GD as a diameter. Therefore, segment GD equals to P1, P2. Next, an avenue of exploration taken was the generalized radius. This was inspired by regular polygons. Notice that the area A and circumference C of a circle have the following formula shown here. Observe the ratio 2A over C. Applying the formulas above and simplifying, we find that 2A over C is exactly equal to the radius. This rule can be generalized for a regular polygon. Consider an n-sided polygon with side length S. The polygon can be divided into n triangles by drawing line segments from the center to each of its vertices. The example for n equals to 5 is shown above. All of the triangles are congruent by SSS congruency. Next, we zoom in on one of the n triangles created to denote this triangle ABC. Each angle in ABC is equal to 2 pi over n, meaning angle ABD is equal to pi over n. Using trigonometry, we obtain the expression that the tangent of ABD equals to segment AD over BD. And because triangle ABC is isosceles, point D bisects segment AC, so AD equals to pi is equal to S over 2. Plugging this in, and solving for A, we get that the apothem A equals to S over tan, 2 times tan of pi over n. Now, because the area of the regular n-gon is equal to n such triangles, A equals to 1/2 SAN. Substituting the expression found for the apothem A and combining like terms, we get the area of the triangle is equal to s squared n over 4 tan times pi over n. The parameter c of the n-sided polygon with side length s is c equals to n times s, and therefore the ratio 2 times area of ABC over c is simplified to this equation, s over 2 times tan pi over n, which is exactly equal to the equation for the apothem. Therefore, the generalized radius rule applies for the Arbelos. So let us take inspiration from this rule and apply it to Arbelos. As such, similarly to a regular polygon, the ratio of 2a over c is equal to the apothem of the Arbelos. Next, consider the center of the axes. Concerning segment AO by the Pythagorean theorem, AO squared equals to OD squared plus AD squared. Now simplifying, we get the result that AO squared equals to R1 times R1 plus R2. Now similarly, the same result can be obtained for BO squared, which equals to R2 times R1 plus R2. When we combine these two equations, we get the formula that AO squared plus BO squared equals AB squared. Therefore, we obtain the result that AOB is a right triangle. Considering right triangles P1, P2D, and ABO. Consider triangles P1AD because its two sides P1A and AD are radius of the center circled at of the circle centered at A. P1AD is an isosceles triangle. Therefore, altitude AX bisects arc P1D. Therefore, triangle ALB and triangle P1, P2D are similar by angle similarity, yielding the following ratio. Substituting the expressions for AO, AB, P1, P2 from prior proofs, we get that P1D squared equals to 4AR1 and P2D squared equals 4AR2. Finally, the main avenue of exploration was the triple tangent inscribed circle. To derive the algorithm needed to construct the triple tangent inscribed circle, which is a tangent circle around here that will be tangent to both of our semicircles, perpendiculars were erected at points S and T and the base of the Arbelos. A prime S was constructed such that A prime S equals to AS equals to R1. Similarly, construct B prime T with B prime T equals to R2. Next, connect these segments A prime T and B prime S. The first thing I noticed was that according to my diagram, point X, which is the intersection, lies on axis GD. So this became the hypothesis that X lies on segment GD. And to prove this hypothesis, let us introduce a coordinate system, shown here, with the origin at S. Our strategy will be to determine the intersections of points of segments A prime T and B prime S with coordinate geometry, then show that this point lies on line GD. The following coordinate values are calculated, and from these we derive two equations for the formulas of lines containing A prime and T and B prime and S. Upon simplifying this equation, because X is the intersection of lines y1 and y2, we set these two equations equal to each other, and upon simplifying, we get that X equals to 2R1. It is apparent that X lies on the axis of GD, so our hypothesis has been proven. Next, we must prove that segment dx is equal to the apothem. The y-coordinate of x can be found by plugging its x-coordinate 2r1 into either y1 or r2. Applying the equation for y2, we get that the distance from x, which is 2r1, and r1, r2 over r1 plus r2, and d, which is dr1 and 0, is r1, r2 over r1 plus r2. Therefore, because this is the above proven expression for the apothem, dx equals to a. Now to construct the auxiliary circle. Construct a circle centered at X with paths through D. Label its points of intersection with semicircles A and B as points E and F respectively. Because the circles has radius dx equals A, radii EX equals FX equals A. Because tangents to a circle from an outside point are congruent, denote segments E prime S equals to E prime E equals to E prime W equals to P. Similarly, this formula holds true. By the Pythagorean theorem, we get that E prime S minus XD squared plus SD squared equals E prime X squared. And upon rewriting this and simplifying, we get the formula that P equals to R1 times R1 plus R2 over R2. Similarly, Q equals to R2 times R1 plus R2 over R2. And notice that E prime F prime has length P plus Q. Finally, using the law of cosines, let R be the radius of the inscribed circle. To find the value of R, observe triangles AMC and ABC. Our strategy will be to find expression for the cosine of angle BAC in both triangles AMC and AMC. Using the law of cosines, then plug in the formula following expressions. The result is an expression 1 over R plus 1 over R1 plus R2 equals 1 over A, involving all the major parameters of the Arbelos. This research paper investigates an inscribed circle that is tangent to all three semicircles. Instead of a single inscribed circle, what if we continue to inscribe circles such that there are an infinite sequence of inscribed circles in the diagram above? Further, what are the properties of the inscribed circles tangent to the axis in two semicircles? It suffices to say the Arbelos allows for numerous values of exploration and yields beautiful results. Thank you.